To be honest, most of the time, these other kinds of functions, if you're asked to do anything with them, they'll be asked you to plot them. Okay, so you would be filling in tables like this. And they could probably give you the x values, you just have to substitute them into the function itself. You can see here that this particular example is 2 to the power x. So an exponential function is where you've got your unknown or your variable x and a power. Okay, so this time it's as a power. They will always look like this or like this. Okay, and majority of the time, well, not the majority, if they are just if they are just 2 to the power x or 7 to the power x or whatever, it's just a number to the power x, then they will always go through this coordinate. That's the coordinate 0, 1. Why will anything of this nature or this form always go through the coordinate 0, 1?
Because anything to the power of 0 is 1.
Exactly, because anything to the power of 0 is always 1. Okay? So whether this number could have been 0.237, it could have been 750. If you've got something to the power of x, you're always going to be going through the coordinate 0, 1. Okay? And if you've got plus 7 after it, then do we remember what happens when you have a number stuck at the end of a general function? It shifts up, awesome. So the whole graph would shift up. So it wouldn't go through the point 0, 1 anymore, it would go through the point 0, 8. Nice. Yes? Does that make sense? Okay. Right. We've talked about asymptotes before. Yes? Remember they are lines that graphs get very, very close to but never actually touch. This will be, this graph would have an asymptote here along the x-axis. It's really tricky, you know, these kinds of graphs are pretty new this year, so we don't really know what kinds of things they're going to ask you. Log graphs, again, we've done the topic of logs. I'm not sure if log graphs would come into this, to be honest. But logs and exponents are inverses of each other, and so if you've got an exponential graph, then a log graph will be its inverse, and we know that inverse functions, do we remember this, are reflections of the line y equals x. Okay, so this would be the line y equals x, this would be the line y equals x. And they would be reflections in that line. I'm going through this very briefly because I don't really think that this is going to come up in your exam. I'm just for glancing over it. And next one. Okay, this stuff is important. So finding x and y intercepts. So to find y intercepts, okay, to find y-intercepts, you're going to replace the value of x with 0. Okay, so that's all you have to do. So if you're trying to find where any graph crosses the y-axis, you substitute the value of x as 0 and find that. Now, if in some cases if there is no answer to that, that means it doesn't cross the y-axis. Okay, so that's what you would do to find y-intercepts. To find x-intercepts, you replace the value of y as 0 and solve. Now we've been doing that lots in the past. For example, when we talked about quadratics, oh Lord, so if we had y equals x plus 2x minus 3, if we were trying to find the the x-intercepts, we already know that they're at -2 and positive 3, don't we? Because what we've done is we've replaced our y with a 0. So in our heads, we would have been able to do that without really thinking about it, but that's what you're doing. You're replacing your y value with 0 and then finding where it crosses the x-axis. Okay? So y-intercepts, put x at 0, x-intercepts, put y at 0.
That's for every graph.
Every graph. Every graph. I'm just showing you that as an example because we've done that so many times before already. Here, take your trash, please. Finding maximum and minimum points. This can be done using the calculator. Okay. So let's have a little bit of a pause. All right. So once you've got your graph in there, you go to Menu, and then you go to Analyze Graph, and we're trying to find the maximum point. So we click on maximum. Now, it gives you information here on the bottom left. It says lower bound ? And you should have some kind of movable line. So what you do is you need to place that movable line on the left of the maximum point. On the left of it, because it's a lower bound. Okay, so that means a smaller number. Then it says, so once you've done that, it says upper bound. So you're going to then move your line so that it covers or shades the maximum point. The maximum point.
I got you.
I don't know what else how else to describe it. No, we're finding the maximum point. No, some people haven't done it. So then I'm going to click there, and look, it's got a big blob on the maximum point, and it's got this coordinate here. We can't quite see it, so I'm going to move it over to here. So this is our coordinate for our maximum point. Negative 1.87, 13.1. Pardon?
I got 2.26 and 21.9.
Then you've got a different function in there.
Maybe you did it wrong.
All right, now if you want to find the minimum point, I'll come and look in a second. If you want to find the minimum point, you do a similar thing, but this time we're going for minimum. Again, it'll ask you for the lower bound. So I can see that my minimum point's here, so I'm going to go a little bit to the left of it, and then a little bit to the right of it, and then it tells me my minimum point is at 0.535, 6.12. Okay, so that's how the calculator can help you find those points.
Why would you find them?
I've said here in capitals, remember for any function you should be plotting on the calculator to see what it looks like. If you're pushed for time, obviously, don't rush this as a checkpoint. But if you're asked to plot any coordinates, if you're asked to draw any graph from a table of values, you ideally would be inputting it into your calculator to have a look what it looks like. Because if you plotted it incorrectly, you're going to lose marks from your coordinates and your plotting. Alright? So please just use it as a checkpoint. Because your calculator, the whole reason we encourage you to use graph calculators is for you to be able to check them. Now on the back page, I've just got a little summary of some common functions for you. Okay? So we've got, if you've got y equals 7, y equals 6, y equals 5, y equals negative 3. We know it's a horizontal line. Okay? So that would be y equals a constant function. A straight line function we know is in the form y equals mx plus c generally. And so that's going to be a sloping line. Quadratic function we know is a parabola. A cubic function. Remember this? D, the cubic function there is your basic cubic function. You've also got the two functions like that. Remember this is where it's a positive and this is where it's negative in front of the x cubed. So many cubic functions actually look like those green ones rather than that basic function. We've talked about this one, the reciprocal function. We haven't talked about the absolute value of the modulus one, it's just there, it was on the same diagram, I didn't bother getting rid of it, so don't worry too much about that. And the exponential and the log function. I then also put down here at the bottom your sine, your cos, and your tan. Do we remember the values for the sine, the cos, and the tan? Obviously this is 0. There are 4 marker points for each of them. Do you remember what increments they go up in? Yeah. Yeah. And you will find that for all of them. Okay, so if you have those initial marker points, you will be able to establish where these values are. So again, this one will be 90, 180, 270, 360. It's a bit tiny on there. 90, 180, 270, 360. Remember the tan function is a bit fancy pants because at 90 there is an asymptote, and then every 180 degrees there is another asymptote. Okay,